If you look at a heavy-duty cycloidal drive,
Yeah.
you know, you see brute force, just solid steel that's designed to take thousands of pounds of
Yeah,
torque.
exactly. It looks indestructible.
Right. But to keep that steel from shattering, engineers can't just make it thicker. They actually have to treat it like a delicate microscopic landscape.
Which is wild when you really think about it.
It is. So welcome to today's deep dive. We're unpacking the advanced mechanical engineering of precision transmissions.
Right. Specifically, how manipulating metal at the micrometer scale is really the secret to building faster, quieter, and, well, stronger machines.
Okay, let's unpack this because, I mean, while terms like residual compressive stress sound really intimidating, the physics behind them are just incredible.
They are, and it really all starts with the exterior of the gears. Specifically, there's this process called superfinishing.
Right.
And the goal here is dropping the surface roughness, what we call the raw value below 0.02 micrometers.
Wow, okay. To give people a sense of scale, a human hair is, what, about 70 micrometers thick?
Yeah, exactly, about 70. So we're talking about smoothing out these microscopic peaks that are thousands of times thinner than a hair.
Just to drastically reduce internal friction.
Precisely. It makes a huge difference.
So is this essentially like, I don't know, using ultrafine sandpaper on wood, but just on a microscopic scale?
Sort of, yeah. But what's fascinating here is its advanced cousin, isotropic superfinishing, or ISF.
Okay, what's the difference there?
Well, ISF is a chemical-mechanical process, and it completely removes directional machining marks.
Wait, so standard machining leaves microscopic grooves, almost like the tracks on a vinyl record.
Yes, exactly like that. And those grooves are a massive liability in a transmission.
Really? Why is that?
Because when planet gears mesh together, those directional tracks actually create high-frequency vibrations.
Oh, which translates to that whining noise you hear in high-stress gearboxes.
You got it. So by making the surface isotropic, meaning it's perfectly uniform in all directions, you're essentially killing that acoustic signature at the source.
You eliminate the vibration before it ever even becomes sound. That is so cool.
It is really cool, but there's a catch with ISF. It takes a lot of time.
Oh, right. Because if you're scaling up production, you can't just spend all day polishing a single ring gear.
Exactly. You need high-speed manufacturing. Processes like power skeeving are used to hit that commercial throughput.
And power skeeving is continuous cutting, right?
Yes, and it can triple your production output. But ripping metal away at that speed introduces vulnerabilities.
It creates weak points.
Right. It heavily compromises the fatigue strength right at the root of the gear tooth.
Okay, well, here's where it gets really interesting. To counteract that speed-induced weakness, engineers rely on residual compressive stress.
Yes, a very crucial technique.
So I'm trying to visualize the physics here.
Yeah.
Is it like pre-compressing a heavy-duty spring so it doesn't snap when operational pulling forces try to rip it apart?
That is a perfect analogy, actually. You're intentionally packing the surface molecules of the metal tighter together before it ever goes into operation.
So it's braced for impact, basically.
Exactly. The metal naturally pushes back against the operational pulling forces, which we call tensile stress, that are constantly trying to rip the gear tooth off during use.
So the surface is actually fighting back against the operational load. It's preloaded to survive.
Yeah, that internal pushback is really the only way these rapidly manufactured gears survive in the field without premature tooth breakage.
So we've essentially engineered this paradox. We have a rapidly manufactured gear with intense internal stress fighting off external loads.
Yeah, there are a lot of forces at play all at once.
But I mean, all that force generates immense heat. If the surface is basically a perfect mirror from the superfinishing, doesn't the lubricating oil just slide right off?
That is the exact problem that laser surface texturing, or LST, solves.
Okay, I've read a bit about this.
It sounds completely wild, but after doing all that work to achieve a mirror finish, engineers use lasers to intentionally blast micrometer-sized craters back into the metal.
Okay, I have to admit, that seems totally counterintuitive. I mean, you just ruined the perfect isotropic surface we spent the first half of this deep dive building.
I know, it looks like damage, but it's highly calculated. Those micropits actually act as tiny pressurized oil reservoirs.
Oh, I see.
Yeah, when the gears mesh under extreme loads, those craters trap the oil. It forces a stable hydrodynamic film right between the teeth.
Wait, so the metal surfaces never actually touch?
Right, they don't touch at all.
They're just hydroplaning on microscopic pools of oil.
Yeah.
That is wild.
It completely changes the game for wear and tear under extreme stress.
Wow. So what does this all mean?
Well, I think it shows that true engineering at this level is invisible to the eye.
Exactly. It means engineering perfection isn't just about the visible machine. It's about mastering microscopic friction, managing those invisible internal stresses, and, designing tiny pools of oil.
Yeah, pools you can't even see with the naked eye.
We started by looking at heavy machinery as brute force steel, but it's really this carefully orchestrated landscape of physics.
It completely reframes how you look at the physical mechanics running the world around us.
It really does. And it leaves you with a wild thought to ponder.
Oh, what's that?
Well, if engineers today are using lasers and chemical baths to optimize gear surfaces down to the micrometer, what happens to mechanical engineering when nanotechnology finally allows us to construct these frictionless gears atom by atom?